All right, final example of max mins. This is one of those brain scratchers that every group of young people, when they get together on a Saturday night, are wondering. It's determine the dimensions of the largest rectangle, having its two lower corners on the x-axis and the upper two corners being contained by that curve. So we want to determine the biggest rectangle. So of course you're always wondering, hey, I wonder how big a rectangle would be when it is under this curve. So here you go. You finally get that mystery solved here. All worth the 4 years of high school math, isn't it? So here's our xy axes, and what we need to identify is we're drawing a rectangle, and it is underneath this shape here. So you do need to know what this shape is, and hopefully most of you see this as a parabola, which is opening down with y-intercept of 16. So end up with a parabola that looks like that. So this question is saying, if we were to put a rectangle inside, what's it going to look like? So it's important that it's on the y-axis because that means that the center of the rectangle is going to be there as well. So if we were to label this rectangle, you'd say this is your length. The whole dimension here is your width, which would mean from the origin to the edge is half a width. So we're on to our second constraint equation here. Or sorry, the second stage, which is the constraint equation. So our constraint equation for this particular scenario, well, it was needed to draw the diagram originally, and it is that parabola that is acting as the constraint equation. So y equals 16 minus x squared. So if I move to stage 3 to figure out, well, what do I want to know? Well, we know the area of a rectangle is length and width. So this is where I got to do a little bit of working my way through it here. The length and width here, I have L's and W's showing up now, and I have X's and Y's showing up. So I've got to consolidate to one system here. So what I'm going to do on my diagram or just over it, I'm going to say, well, the half W, that's really equal to the x coordinate for that point of intersection. So it's equal to x, and my L then, well, that's just the y value. So I'm going to make the adjustment appropriately in my formula here. So it doesn't matter which way you go with this. You can switch the constraint equation if you choose, or the optimization equation. So I'm going to use the optimization equation. So the length is going to be a y. Now be careful with the width. Remember the width. The width isn't the half w, all right? It's actually going to be 2x, all right? Because half w is equal to x. Well, if I want the full w, it's going to be 2x. So that means my area is 2xy. So there is the equation that we want to optimize. And the constraint equation's already in the proper form. It is y equals. So we're all set to go here with the substitution. So 2x bracket 16 minus x squared. So we end up with 32x minus 2x cubed. Now we're going to take the derivative. At this point, all the hard work is done. You've honestly done all the thinking part right there. The diagram, setting up the constraint equation, setting up the optimization equation, that's what's needed in order to solve this question. So we got 32 minus 6x squared. We let dA by dx equals 0. So 0 equals 32 minus 6x squared. 6x squared equals, 32. So x will equal the square root of 32 over 6. All right. So there is our, that is the value of our x. So there we go. Over here then, we can find the corresponding y value. So y equals 16 minus, now x squared is just 32 over 6, remember? Okay. And that comes from this line right here. X squared will be 32 divided by 6. So if we want to find the dimensions then, so therefore the base width will be, now remember this x value, this x is only half the width, so we're going to have to double it, so it'd be 2 times root 32 over 6 units by, the y value is all right, 16 minus 32 over 6 units. There you go. That is the dimensions for the largest rectangle that will fit inside the parabola and the x-axis. All right, on to the next one. And just before I go to that next example, you're now able to do the textbook work on page 188. So as we go through, like I said, you're still able, you don't have to watch all the videos at once. You're able to watch them piecemeal and keep up with the work. And now we head into our final section here, trig and exponential functions. So it's the same goal again. We are using our understanding or knowledge of derivatives to solve the real world problems. And we're looking at one specifically involving trig and exponential. So we're going to start off right with a trig question here. So 2 rods, 15 centimeters and 10 centimeters long, are hinged at one end, and the other end's connected with an elastic. So what we have going on here is we have a hinged end and a hinged end. So this one's behind, and we have some form of elastic wrapped around the end of it. And let's make this one 15 centimeters, this one 10 centimeters. If the hinged corner's angle is increasing, all right, so if it's increasing, that tells me that it's going to be a positive value, and it is 0.01 rads per hour. So yes, we are back into radians. We don't have to do a lot of work for the people that are sitting there moaning and groaning about it. So we know that is 0.01. And what is that? If the angle is increasing, we are now talking about the change in the angle, d theta by dt. So we know d theta by dt. All right. Determine the rate of change of the area. So we are looking for the change of area when the angle is pi by 4. So when theta equals pi by 4. So this is not it's not a max-min question. All right, we're looking for a specific value. So that means I don't have to do the constraint equation, optimization equation. So there's going to start getting mixed in here. What am I looking for? Well, I'm trying to find area for this triangle, 1/2 base times, base times height. That's our comfortable formula with the triangle. All right, so some information here. Going back to my diagram, the height of this triangle, right here, h, if this angle in here is theta, I can find h by taking that component, the y component. So if you remember back to your vectors, and I'll continue in green down below here, if I use that triangle that I've outlined in green, it is a right angle triangle. So I'll maybe just give it a quick sketch down here. I've got this as 10 centimeters, this is theta, this is h. If that's my reference angle, I'm going to be using sine. So sine theta equals opposite over hypotenuse. Sine theta equals h over 10. So the height of this triangle at any point in time is 10 sine theta. And that's going to be measured in centimeters. So I do know the height of the triangle. All right, and our base, of course, is the one that's along the bottom here. So the base is 15. So I can plug this information in. So area equals 1/2. The base is constant. It's not changing, so it's going to be 15. The height is going to be 10 sine theta. And theta is the variable here. All right, so simplifying that, 1/2 of 10 is 5. And then we have 5 times the 15. What do we end up with? 5 times 15, 75. 75 sine theta. So there is the function or the equation for the area of this particular triangle. We want to know the area when theta is equal to pi by 4. And we're trying to find the rate of change of area. So we are looking for dA by dt, rate of change. So that's really the unknown, and we can add that down here. That's what we're looking for. And that's equal to 75, and the derivative of sine is cos theta. And we took the derivative. Remember, theta is a variable, d theta by dt. So we have all the information of interest here. Well, we're looking for that. 75 is a number. We know theta, it's pi by 4, and we know d theta by dt. So we have all the information necessary to solve this. 75 cos pi by 4, d theta by dt, 0.01. Cos of pi by 4, that is 1 over root 2. That's your special triangles. So 75, 1 over root 2 times 0.01. And we can just leave it as 0.75 over root 2 for now. What's the units? Centimeters squared per, and I think time was in hours, so there we go. So therefore, the area of the triangle, the area of triangle is increasing at 0.75 over root 2 centimeters squared an hour. All right, so the same process as earlier related rates. The only difference this time is theta is going to be the variable that we're going to be working with. So I'll continue or hopefully finish with the last video.